Dear spectators, this video presents the article Accelerating Metric Filtering by Improving Bounds on Estimated Distances, which is published in the proceedings of the SISAP conference. My name is Vladimir and I wrote this article together with my professor Pavel Zezula. We both work at the Masaryk University in Brno, Czech Republic. I start extraordinarily with a summary of our article. We enhanced the definition of triangle inequalities to define tighter bounds on unknown distances. Our approach applies to all metric spaces and thus achieves huge applicability. Filtering based on triangle inequalities can be used together with many similarity indexes to speed up the search practically for free. The example is given by the PM3 of Tomáš Skopal et al. This article addresses the similarity search in metric space, and this is the only restriction on the search data. We denote capital D the domain of the searched object, and D is a distance function that expresses the dissimilarity of objects. The distance function must meet four properties including the triangle inequality. We denote by X the searched dataset and Q is the query object. The goal is to efficiently find the set A and S of the most similar objects to Q in X. Let's pick three objects Q, P and O from the domain. As the notation suggests, they are going to be the query object Q, a reference object P, so-called pivot, and object O from the dataset. Further, we assume that the distances PQ and PO are already evaluated, while the distance QO is unknown. In this case, the triangle inequalities define the upper bound and a lower bound on the unknown distance. These bounds can be used for so-called metric filtering. Let's assume that we are interested just in objects O within the distance R to Q. Then, if the upper bound on the distance QO is smaller than R, O is in the query answer for sure. Therefore, it does not have to be accessed, and its actual distance to Q does not have to be evaluated. Similarly, if the lower bound is bigger than R, O cannot be in the query answer, and thus its accessing as well as the distance computation can be skipped to speed up the similarity search. However, when having bounds on distances, their tightness is crucial. The tightness of the bounds on distances given by triangle inequalities suffers from the dimensionality curse. The extreme cases are given by equilateral triangles. The lower bound on each distance is 0 and thus ineffective for the filtering. The upper bound is twice as big as the actual distance. In our article, we enhance definitions of triangle inequalities with additional information to improve the tightness of the bounds on unknown distances. Moreover, we define a new lower bound on distances in metric spaces. The rule of the triangle inequality allows to isometrically embed any three objects Q, O, P into two-dimensional Euclidean space. In this space, we can evaluate angles in the triangle with vertices Q, O, P using the cosine rule. Therefore, please notice that the analysis in this article is valid for all metric spaces, since we always consider just one triangle. Further, we simplify the notation to have a triangle with sides A, B, C, where C is the only unknown distance. We denote alpha, beta, gamma, the angles that are opposite to corresponding sides. Let's thus analyze the extreme case when the bounds on C are tight. The upper bound is tight if C equals to B plus A. It means that gamma is the straight angle, alpha is 0 and beta is 0. The lower bound is tied in two cases. In the first one, beta is the straight angle, alpha is 0 and gamma is 0. In the second one, alpha is the straight angle and the other angles are 0. To sum it up, there must be two zero angles and the straight angle in a triangle to make any of these bounds on C tied. The question thus arises: how often do we have a triangle with such angles when searching in real-life metric spaces? The answer is practically never when searching in contemporary data. To give an example, we visualize angles sampled from real-life data, which are the visual descriptors of images from a neural network. We have randomly selected 333,333 triplets of objects to evaluate almost a million angles in triangles. The sizes of triangles are depicted in this plot at the x-axis. The y-axis depicts the number of triangles of the corresponding size in the sample. Please notice that it uses the logarithmic scale. You can see that all the sampled angles are of sizes between 21 and 91 degrees. While we thus admit all possible sizes of angles alpha, beta, gamma when searching in spaces with so limited angles in triangles of objects, the core of the article consists of the following thoughts. The upper bound on C is given by a sum of distances A and B. We prove that distance C is equal to a sum of distances A and B multiplied by this function of angles alpha, beta, gamma. Similarly, the lower bound on C is given by a difference of B and A. We prove that distance C is equal to a difference of B and A multiplied by another function of angles alpha, beta, gamma. There is a special case for this equation. If B equals to A, then the right side of the equation forms an indefinite expression, since it equals to 0 multiplied by infinity. This is a correct feature of this equation, since if B equals to A, then C cannot be expressed using the zero difference of B and A and the sizes of angles alpha, beta, gamma. Let's assume that angles alpha, beta, gamma are of limited sizes, and let's denote omega min and omega max, the bounds on these angles. Having these bounds, we prove that they limit the values of fractions used in equations 1 and 2. We point out two features of bounds omega min and omega max. First, they always exist, as omega min is trivially 0 and omega max is trivially 180 degrees. Second, these bounds on angles are meaningful if and only if omega min is between 0 and 60 degrees and omega max is between 60 and 180 degrees. This limitation is given by a fact that they limit angles in a triangle in a Euclidean space, where the sum of three angles is 180 degrees. Let's focus on equation 1. We denote CLB sum, the minimum possible value of fraction in equation 1. The notation suggests that this value defines the lower bound on C, which is based on the sum of A and B. Similarly, we denote CUB sum, the maximum possible value of fraction in equation 1. This value defines the upper bound on C, which is based on the sum of A and B. Then we have also equation 2. Therefore, we denote CLB diff, the minimum value of fraction in equation 2. This value defines the lower bound on C, which is based on the difference of A and B. Finally, we denote CUB diff, the maximum value of fraction in equation 2, and it defines the upper bound on C, which is based on the difference of A and B. As you see, we put all these coefficients in a green color. The reason is that we provide algorithms to evaluate all these coefficients for arbitrary given angles limitation omega min, omega max. There is just one trivial case formed by CUB diff. This value is infinity for all meaningful ranges omega min, omega max. Therefore, the upper bound on C based on the difference of A and B is infinity for all meaningful ranges omega min, omega max. It is easy to prove that no other upper bound on C can be defined using angles limitation and a difference of B and A. The theoretical contribution of this article is thus the following. We define two lower bounds and one upper bound on a distance C in a triangle with sides A, B, C. These bounds exploit the range of permitted angles and distances A and B. Let's discuss first the trivial examples of angles limitation. If omega min is 0 and omega max is 180 degrees, then the upper bound and lower bound on C is the same as in case of pure triangle inequalities. The newly derived bound based on the sum of A and B is 0 in this case, and therefore ineffective for metric filtering. If we set omega min equal to omega max equal to 60 degrees, then it means that all triangles A, B, C are equilateral. Therefore, if we know the sum of A and B, we immediately know that C is equal to 1/2 of this sum. Let's have a look on the bounds that we derived. The upper bound on C based on the sum of A and B is tied. Also, the newly derived lower bound on C based on the sum of A and B is tied. And the last lower bound on C based on the difference of A and B is not defined, as it is equal to indefinite expression. Here are the examples for non-trivial angles limitation omega min, omega max. Let's discuss one concrete example. For angles from 30 to 80 degrees, we can guarantee that the upper bound based on the sum of two sides can be decreased by approximately 31%. The lower bound based on the difference of two sides can be almost doubled, and we can establish a new lower bound on C based on the sum of A and B. Please notice that these bounds are precise as far as the angles limitation is guaranteed. Let's move towards to real-life usage. Metric space similarity models usually do not guarantee angles limitation omega min, omega max beyond trivial values 0 and 180 degrees. However, we can still set the angles limitation experimentally using data sampling. Then we are losing the certainty that the newly derived bounds on C are correct. We dedicate a whole section of the article to clarify the consequences of the imprecise angles limitation omega min, omega max. We prove that all newly derived bounds on C can be correct even in a triangle that violates the angles limitation omega min, omega max. Moreover, we prove that all three bounds on C can be correct at the same time, even in such triangle. These features lead to a question: when are the newly derived bounds on C correct and when they are not? We properly define three functions in the article, one per each bound on C. These functions define triangles for which is the newly described bound on C correct, wrong, and tight, respectively. The correctness of all new bounds on C is given just by the angles alpha and beta, which enables us to visualize the classes of triangles. Formally saying, we introduce the decomposition of all triangles into several classes. To facilitate this step, we add one more assumption. We assume that B is bigger or equal to A, and thus beta is bigger or equal to alpha. Please see that this assumption is made without a loss of generality for the similarity search, since we consider just one triangle ABC. Specifically, if B is smaller than A, we can swap the notation of vertices Q and O. While this preserves the distance C thanks to the symmetry of distance function, it swaps distances A and B. To visualize the decomposition of triangles ABC, we introduce plots like this one to depict all possible triangles as single points. Here the x-axis depicts the angle beta, the y-axis depicts the angle alpha, and black lines limit the area of triangles, since beta is bigger or equal to alpha, and the sum of alpha and beta is at most 180 degrees. Therefore, please focus on the triangular shape in the plot. Let's assume that angles limitation omega min and omega max is given, for instance as 30 and 80 degrees. We derive the blue, green and orange functions that are depicted in the plot, and their semantics is as follows. First, let's focus on the function depicted by the blue curve. If a triangle is represented by a point which is above or on the blue curve, then the lower bound on C based on the difference of B and A is correct. If a triangle is represented below the blue curve, then this lower bound on C is wrong. If and only if a triangle is depicted on the blue curve, then the lower bound on C is tight. Now let's focus on the function depicted by the green curve. If a triangle is represented by a point above or on the green curve, then the upper bound on C based on the sum of A and B is correct. If a triangle is depicted below the green curve, then this upper bound on C is wrong. If and only if a triangle is depicted on the green curve, then the upper bound on C is tight. Finally, let's discuss the orange curve. If a triangle is represented by a point below or on the orange curve, then the lower bound on C, based on the sum of A and B, is correct. If a triangle is depicted above the orange curve, then this lower bound on C is wrong. If a triangle is depicted on the orange curve, then this lower bound on C is tight. This visualization can be used to select a suitable angles limitation omega min, omega max for arbitrary metric space. Specifically, we need to select angles limitation that implies the blue, green and orange curves that tightly embrace the points depicting triangles sampled from the data. Let's visualize the real-life data. The purple points in these plots represent the triangles made of triplets of visual descriptors of images. We examine the decaf descriptors from a neural network and well-known SIFT and MPEG-7 descriptors. The decaf and SIFTs are compared by the Euclidean distance. The space of MPEG-7 descriptors is made as a combination of 5 metric subspaces, mostly L1 and L2 spaces. These plots illustrate that it is possible to select omega min and omega max for each dataset to tightly embrace the sampled triangles by blue, green and orange curves. However, we are interested mainly in the similarity searching, and thus in triangles where distance C is extremely small. These extreme triangles are not effectively sampled when picking triplets of objects randomly. Therefore, we introduce another data sampling for the application of the bounds for similarity searching. The black circles in this plot represent the triangles in which C is the distance of Q to each of its 100 nearest neighbors from the sample of dataset X. Since distance C is extremely small, also the angle gamma tends to be small, and thus these points are shifted to top right. For this reason, mainly the lower bound based on the sum of two distances is dangerous in the application of the similarity search. Please focus on the orange curve in the plot. When setting the bounds omega min and omega max to embrace these points, the semantics of the angles alpha, beta, gamma is not the same anymore, and it causes the need for independent selection of omega min and omega max for each of the newly proposed bound on C independently. We plan to define the analytical approach to select the bounds omega min, omega max for each of these bounds on C as the future work. For now, we pick them to embrace the sampled triangles tightly. These plots thus visualize the color curves that are introduced by the angles limitations, and we summarize the newly derived bounds on C in the following slide. Here. The lower bound based on the difference of B and A is thus increased by 66, 26 and 16% in case of decaf, SIFT and MPEG-7 descriptors respectively. The new lower bounds on C based on the sum of B and A are established, and the upper bound on C based on the sum of B and A is decreased by 32, 24 and 29% respectively. How perform these bounds on distances when exploited for the metric filtering? First, we compare the number of saved distance computations when filtering with pure triangle inequalities and with the newly proposed bounds on distances. We use 256 pivots, 1000 query objects, and we search for 10 and 100 nearest neighbors. We use box plots to depict the number of saved distance computations over particular query objects. We evaluate k nearest neighbors queries as range queries using the distance to the current kth nearest neighbor as the query radius. We examine all three datasets of image descriptors. These box plots present the results for 10 and 100 nearest neighbor queries respectively. The y-axis depicts the number of saved distance computations, dark box plots depict the results of the filtering with pure triangle inequalities, and light box plots depict the results of the newly proposed bounds on distances. As you see on the left side figure, the median of the saved distance computations in case of the 10 nearest neighbor queries increases from approximately 0 to 12%, from 59 to 75%, and from 65 to 80% in case of the decaf, SIFT, and MPEG-7 descriptors, respectively. These results are coherent with the results of the 100 nearest neighbor queries. The query evaluation with the newly proposed bounds does not guarantee precise results. Some true positives can be filtered out by lower bounds, and false positives can be added by the upper bound. False positives are added also due to the gradual shrinking of the search radius. Nevertheless, 999 answers out of 1000 that are returned for the 10 nearest neighbor queries contain all 10 true nearest neighbors, in case of all datasets. The recall of these queries is thus 1. The median size of query answers is 10, again for all datasets. The answers for 100 nearest neighbor queries contain all true positives in case of 955, 963 and 923 query objects, speaking of particular datasets. The biggest answers are returned in case of MPEG-7 descriptors. Their median size is 105 objects. The overall precision of the newly derived bounds on distances is thus admirable. Thank you for watching this presentation.